Okay, hello. Welcome everyone. Today we are focusing on this particular chemistry problem. So the problem is on the board. Please take about a few seconds, take about half a minute maybe to read the question. So it's a question pertaining to stoichiometry, empirical formula, and a little bit, combustion reaction. So I'm going to read the question. 0.5438 grams sample of a compound known to contain only carbon, hydrogen, and oxygen was burned completely in oxygen, right? The products were 1.0390 grams CO2, 0.6369 gram water, and we have to determine the empirical formula of the compound, right? So if you remember, normally when we are solving empirical formula and molecular formula determining questions, we are mostly given the percent abundance, right? We are given certain percent carbon, certain percent hydrogen, and certain percent oxygen in that particular compound. But in this case, instead of those percent composition or abundance, uh, we are given the total mass of the compound, which is undergone combustion reaction, and we are given mass of CO2 produced and mass of H2O produced. Okay, so this is a little bit different. So what I'm going to do is I'm going to write the general combustion reaction. So I'm going to say CXHY and OZ uh, plus NO2, because I don't know how many moles of oxygens are used, right? I also don't know how many atoms of carbon, hydrogen, and oxygen are present in that particular organic compound. I just know there are carbon, hydrogens, and oxygen, which is very clearly, mentioned in the question. So the product, I'm gonna say it's gonna be A moles of CO2 and B moles of H2O. Okay, so this much I know. This is a very generic uh, equation without the actual coefficients. And the question also gives us how many grams of CO2 are produced and how many grams of H2O are produced. So this is somewhere we have to be really careful. So if you look at the reaction, so if you look at just the CO2 in the product, all this carbon, all the carbon in the CO2 is coming from your organic compound, not from the oxygen that is used in the combustion, right? And all the hydrogen in the water molecule, it's also coming from the uh, organic compound and not from the oxygen used in the combustion. So what I'm going to do is I'm going to use the mass of carbon dioxide that's given to us. I'm going to convert that into the moles of CO2. And from the moles of CO2, I can get moles of carbon. And from there, I can get grams of carbon, right? And that grams of carbon would be the carbon present in my parent compound. And I'm going to do this very similar thing from water for water. I'm going to take the mass of water that was produced. From there, I'm going to get moles of water. From there, I'm going to get moles of hydrogen and then the grams of hydrogen. That would be the grams of hydrogen contained in my parent compound. And after that, I'm going to add the mass of carbon and mass of hydrogen and subtract that from the total mass of the compound. That's going to give me the mass of oxygen. Okay. So that way I have mass of carbon, mass of hydrogen, and mass of oxygen in the parent compound. And from there I can, do the moles calculation and then find the empirical formula. One thing to be careful right here is we can't use the mass of water to determine the mass of oxygen, because you can see the oxygen in the product is not only coming from the organic compound, it's also coming from the oxygen used in the combustion. So we can't do that. We can use the CO2 for carbon. So what I'm going to do is I'm going to circle this and I'm going to use this for evaluating the mass of carbon. I'm going to use the water molecule for evaluating the mass of hydrogen and not oxygen. Okay, so let's begin our calculation. So I'm going to start with 1.0390 gram CO2 times, I'm going to convert this into moles. So 1 mole of CO2 on top, and the molar mass of CO2 is 44 grams CO2. So that's what I'm going to write on the bottom. And from there, I'm going to go to 1 mole of CO2. For each mole of CO2, we have 1 mole of carbon. That's from the molecular formula. If you take a look at the molecular formula of CO2, for 1 mole CO2, there is 1 mole of carbon atom, right? And from the mole of carbon, I'm going to convert this into the grams of carbon. 1 mole of carbon is basically 12 grams of carbon. So if you cancel the units, grams of CO2, grams of CO2 cancel, moles of CO2, moles of CO2 cancel, moles of carbon and moles of carbon cancel. So this is going to give us around, let's see how much I have, 0.2834 grams carbon. Okay. So I have the grams of carbon now. So I'm going to do similar thing for the grams of H2O, 0.6369 grams H2O. I'm going to convert this into moles of H2O. So 1 mole of H2O on top. The molar mass of H2O is around 18 grams. And then from moles of H2O, 1 mole of H2O, I'm going to find moles of hydrogen atom, and that's 2 moles of H. This is hydrogen atom, remember. Number of atoms is important for empirical formula and molecular formula kind of calculation. Not the molecules, the moles of hydrogen atom. And from there, 1 mole of hydrogen atom is very close to 1 gram hydrogen atom. So if you do the calculation, you'll get around 0.0708 grams hydrogen atom. So I try to take as many decimal places as possible because calculations like this tend to be uh, very particular about number of decimal places. So around 4 decimal places is more than good enough. So I have grams of carbon, I have grams of hydrogen. What about grams of oxygen? So I'm going to take the total mass, 1.0390, and I'm going to subtract the mass of carbon, 0.2834 grams. So this is also grams. Make sure to track the units. 0.0708 grams hydrogen. So this is going to give me around, let's see how much I have for the oxygen atom. So 0.1896 grams of oxygen atom. Okay. So now we have grams of carbon, grams of hydrogen, and grams of oxygen. So what I'm going to do is I'm going to convert the grams of carbon into moles of carbon. So what I'm going to do is 1 mole of carbon on top, divide that by 12 grams carbon. That's going to give me around 0.0236 moles of carbon, not grams, because we need moles. And for grams of hydrogen, I'm going to do 1 mole of hydrogen on top, and oops, 1 mole of hydrogen is around 1 gram hydrogen, so this is 1 over 1, so it's the same number, 0.0708 moles hydrogen. And for oxygen, I'm going to do times 1 mole of oxygen. This is atoms, so that's going to be around 16 gram of oxygen, and that's going to give me around 0.01185 moles of oxygen. Okay, so now I have moles of carbon, moles of hydrogen, and moles of oxygen. And to get the empirical formula, we have to get the whole number atoms. So what I'm going to do is, out of these 3 moles, the smallest number of mole is the moles of oxygen. So I'm going to divide all of these moles. For carbon, I'm going to divide the moles of carbon by the smallest number of moles, which is moles of oxygen. So 0.0236 divided by 0.01185. So that's going to be around 2. You'll get very close to 2. For hydrogen, I'm going to divide 0.0708 by the smallest number of mole, which is again 0.01185. That's around 6. And for oxygen, which is basically 0.01185 divided by the same number, because that's the smallest number of mole, and that's going to give me around 1. So I have all whole numbers, 2, 6, and O. So my empirical formula is going to be C2H6O, right? So you can imagine what that might be for, just by the look of the Look up the formula based on the number of carbon, hydrogen, and oxygen. There are multiple possible organic compounds. So this is how you would approach, problems like this. When the question is not giving you directly the percent carbon, percent hydrogen, and percent oxygen present in your organic compound. Instead, the question gives you the total mass of the compound and gives you a combustion reaction and gives you the mass of carbon dioxide and mass of water released. Follow this procedure, and this question has been asked in the IBDP questions in the past, so this tends to be very important. And good luck.